Hello, I am Mehmet Arda Yıldırım from Bilkent University Physics Department, and this is my Physics 212 Modern Physics project video presentation. In this project, we investigated a quantum circuit operator, namely Hadamard gate, and compared the noise due to increasing outnumbered gates applied to a single qubit. Further, we built the analogous operator in classical means, as an outnumbered subsequential array of simple signal adder-subtractor circuit with a specific resistor arrangement to simulate the normalization constant. So we had two analogous quantum and electrical operator to compare the noise between them. In the canonical basis of qubit states, the Hadamard gate has the following matrix representation. The 1 over square root 2 in the front accounts for the normalization. A qubit purely in the ket0 state will transform into the equally distributed superposition of ket0 and ket1 states. The primary fascinating property of this operator is that it is both unitary and symmetric, which makes its square equal to the identity. In other words, applying this operator twice spits out the original qubit state. Utilizing IBM Quantum Platform, the following code was implemented using Qiskit library of Python. This builds the quantum circuit in the provided image. The barrier operations in between each and every pair of Hadamard gates are implemented solely with the aim of keeping the Hadamard operator pure and away from any readily enforced optimization. We choose the quantum processor unit called IBM PHYS due to comparably low operation traffic. The circuit is run 5 times with a number of 2 raised to the power of 13 shots in each run. We gathered the following quantum data. After some basic calculations, the deviations of each qubit from pure 50-50 state are found to be as the following. As mentioned, we also constructed analogous electrical operator as a signal adder-subtractor circuit with the provided diagram. We utilized iron soldering for cleaner placement of devices. With 2 signal generators connected to the start, we are able to simulate the canonical basis representation of the qubit as the components of the 2-dimensional spinner. For pure ket0 state, we give 1 volt AC signal as the upper input and 0 volt AC signal as the lower input. We measure the voltages in the outputs of the operator. With the components of the spinner are measured, we gathered the following data. We can simply calculate the fidelity values from the square of the components, which will represent the probability distribution of this electrical system. The calculated fidelity values are as following. From these fidelity values, the noise in the electrical system are calculated to be as such. Comparing the noise in both data, we see the trend of the sequence in which highest number of operators are applied, having the highest noise in both systems. However, the reason electrical system has more noise than the quantum system can be explained with the instability of this fresh field of physics. The quantum technologies are yet to be improved and stabilized. Currently, they cause some unexpected results, as in this project, alongside any additional possible stochastic error.